Hello everyone, today we are going to talk about one of the most important ways to prove statements in mathematics, which is called proof by contradiction. Okay, before I start, let me ask you, what is a proof? We always talk about proofs of this and that, but what is a proof? So in mathematics, when you say proof of a statement, it means a sequence of logical deductions from some axioms which shows that the hypothesis that we have guarantee the conclusion that we want. Okay, so let me start with an example. So let's take two integers m and n. Let m and n be two positive integers such that m is less than n. Okay, so you have two positive integers m and n, and m is less than n. And then what you want to prove is this: show that or prove that m squared is less than n squared. Okay, now here, how many things do we have as hypothesis? We have basically two things. Number one is m and n, they are positive integers. Okay, so we have the following hypothesis. M and n are positive integers. Okay, that is the first hypothesis, and there is a second one. What is that? M is less than n. Okay, and m is less than n. Okay, so these two are our hypotheses, and we want to reach to a conclusion. And what is the conclusion? The conclusion is that m squared is less than n squared. Okay, so conclusion is this: m squared is less than n squared. So this is a mathematical statement. It gives you these two hypotheses. These two things are true, and you need to make sure that the a thing that you want is also true. So a proof is a bridge between these two things. You have to start from here, and then you need to end there. Okay. And the question is, what is this bridge made of? It's made up of feelings, hyperboles, tails? No. Okay. A proof is made up of arguments, mathematical arguments, logical deductions. Okay. So let's see how we can prove this thing from those two hypotheses. Okay. So this is how we're going to prove it. Notice what we have. We have m is less than n, right? We have m is less than n, right? And we also have m a positive number, right? So now if you have an inequality, and if we multiply both sides by a positive number, what happens to the inequality? It does not change, right? So that means m squared is less than m times n. And why is this true? This is true because m is a positive number. Okay, let me give this inequality number 1. Now similarly, we can get another inequality, starting from the inequality m is less than n. Similarly, m is less than n, that means m times n is less than n times n, which is n squared. So in this case, we are multiplying both sides of this inequality by n. And this will also preserve the inequality because n is a positive number, okay? So let's give it a name, 2. And why is it true? Since n is a positive number. Okay? Now if you combine these two statements, inequalities, in the first one we have m squared is less than m times n, and in the second inequality we have m times n is less than n squared. And therefore, what do you have? M squared is less than n squared. Okay, that's the end of the proof. That's how you prove it. Okay. This is a very simple proof, and also this is something that is called direct proof. Direct proof means you start from the hypothesis and if you keep arguing and arguing until you get the conclusion. Okay. So that's called a direct proof. But in reality, sometimes it's not easy, or sometimes it's not even possible to make a direct proof. And so mathematicians have created different kinds of ways to prove things. Not just mathematicians, also logicians, philosophers, they have developed these things. But in mathematics, we definitely use very powerful techniques. One of them is called proof by contradiction. Okay, so proof by contradiction does not go directly from the hypothesis to the conclusion. It changes the statement a little bit and then prove that thing. So let me give you an example, a very simple example of a proof by contradiction. So right now we're going towards proof by contradiction. So let me make this title, proof by contradiction. Let me start with a very simple example. Okay. Let m be an integer such that m square is even. Okay. So that's your hypothesis. What is it? M is an integer and also m square is even. And what is the conclusion? Prove that m is also even. Okay. Now, what is an even number? A number is even if 2 divides that number, right? For example, 4 is even, 20 is even, right? But 15 is not even, because if you divide 15 by 2, you have a remainder of 1. Okay, so 2 does not divide 15, so 15 is not an even number, 15 is odd. Alright, now here, what we'll do is this. We'll not directly go to our conclusion that m is even. We wanted to get there, right? M is even. But let's say that becomes false. Now what is the opposite? What can happen if an integer is not even? What possibilities do we have? Yes, exactly. So if it is not even, then it has to be an odd number, right? So let's suppose on the contrary, that m is odd. Okay, and as we told a few minutes ago, that if a number is odd, then if you divide that by 2, you always get a remainder of 1, right? So we can write every odd number as this. Therefore, m equals to 2k plus 1, where k is some integer. Right? For example, m is 1, then we can take k to be 0, right? 2 times 0 plus 1 is just 1. Suppose m is 5, then we can take k to be 2, right? So this is 2 times 2 plus 1 is 5. This way we can write every odd numbers, odd integers, okay? All right. Now if this is m, then what is m squared? This is 2k plus 1 whole square, right? And if you FOIL this thing, what do you get? You get 4k squared plus 4k plus 1, right? And notice this term has a factor of 4, so definitely you can divide this by 2. This term 4k, that has a factor of 4, so definitely you can divide that by 2. But you have here 1, and you cannot divide 1 by 2. In other words, if you divide this m squared by 2, you have a remainder of 1, right? And hence 2 does not divide m square. i.e., if 2 does not divide a number, that means that number is odd, right? i.e., m squared is odd. But at the beginning, what did we have? We had that m squared is an even number. That was our hypothesis. We cannot change our hypothesis, right? So at the beginning, we agreed that m squared is even. But then, if m is odd, then m squared is forced to be odd, which is not possible, okay? Which is a contradiction. Okay? And therefore, what happens? m cannot be odd, right? Because if m becomes odd, then it creates trouble. Therefore, m cannot be odd. Okay? Now a number, an integer that is not an odd is definitely an even integer, right? And hence m is even. Okay? So this is an example of proof by contradiction. So how did we prove this thing? Actually, notice the very first thing is that we have changed our conclusion. So what we had as our conclusion, what we wanted is m to be even. We went completely the opposite. So this kind of a statement is called contrapositive. Okay? You wanted to show that m is even, right? You went to its opposite. What is that? That m is odd. Okay? Now you play around with this new thing that m is odd, and then you will keep going and keep going until you break up something, some of the hypotheses. Okay? So in this case, one of our hypotheses was m squared is even, and then we broke that hypothesis. But that's not allowed. Okay? So that means this statement cannot be true. That m is odd, that cannot be true. That creates problem. Okay? And we created this contradiction to show that it creates problem. And that says, okay, m is not odd, and therefore m is even. Okay, so that's how proof by contradiction is made. Okay, you change your conclusion completely to the opposite, and then you play around with that thing until you arrive at some contradiction. Okay, and that shows the contrapositive statement that you started with is false. Therefore, the original statement is true. Does that make sense? I hope it does. All right, so let's go to something which is a very classical application of proof by contradiction, and it had tremendous history. So long time ago, actually, people did not have the idea of irrational numbers. They only knew about integers, and then they knew about fractions, rational numbers, right? But then something happened, something very bizarre happened in the Greek world, and here it is. So from Pythagoras' theorem, we all know this thing, right? If we have a right triangle, and then if we draw squares on the sides adjacent to that right triangle, the summation of those two areas will be equal to the area of the square having this side equal to the hypotenuse, right? Okay. In other words, if this is A, this is B, and this is C, then C square equals to A square plus B square, right? But now suppose you take a square of length 1. Okay, then what happens? Suppose we take a square of length 1. So this is 1, say, feet, or whatever you need, meter, doesn't matter. And this is also 1, and you create this square, right? You can definitely make that. And then you can create the diagonal, right? Okay. But then what is the length of this diagonal? Well, I mean, now you know this is the square root of 2, right? So according to Pythagoras, if this is C, then C square equals to 1 square plus 1 square, which is 2, right? So that means C equals to square root of 2. But what is this guy? In the ancient world, people had no idea what this thing is, because if you want to calculate square root of 2, then if you write this as a number with decimal expansions, you can keep writing and writing and writing. It will never end, and there will not be any pattern that repeats. That completely says that this cannot be a rational number. Okay? But then somebody proved that it is not possible that a square root 2 is a rational number, and that proof was amazing, and let me show you that proof. But first of all, I want you to know that square root of 2, that's a length, right? So there should be a number which gives this length. All right, now here's the thing. Prove that the square root of 2 is an irrational number. Okay. Irrational means it is not rational. Irrational does not mean it is mad or eccentric. Right. So proof. We want to show that root 2 is not rational, right? And if we follow our previous proof, what did we do? We went completely to the opposite statement, the contrapositive thing, right? So root 2 is not rational. What is the opposite of that? That root 2 is rational. Okay? So that's our starting point. We'll start from the contrapositive of that. Okay? So let's suppose root 2 is a rational number. Okay. Now, what is a rational number? It is some integer over some other integer. Okay. So definitely, if it is a rational number, there should be two integers. Let's say m and n, so that square root of 2 is equal to m over n, right? Hence, there exist two integers Actually, we can simplify this thing. We can just assume those two integers are positive because square root 2 is positive, right? There is two integers, m and n. N such that two things. First, our square root of 2 equals to m over n, right? Okay. Because square root 2 is a rational number, as we have supposed, so there should be some numbers like this, right? Okay. Now, notice this thing. This is a very simple thing. We all know this. Suppose we have 1/2, and then we have 2/4, we have 3/6, okay? We have 20/20 over 40/40, right? They look different, right? So the numerator and denominator are different in both cases. In all the cases, right? Here it is 1, here it is 2, 3, 20/20, and then we have 2, 4, 6, 40/40, right? Those m and n, they are different, that's true. But you can notice they all mean the same thing. 2/4 is 1/2. So is 3/6. So is 20/20 over 40/40, right? Okay. So we can assume just this case. This is called the normal form. Okay. So what does this normal form mean? It means that the numerator and the denominator, they don't have a common factor. For example, let's take this 2 and 4, right? They both have a common factor of 2. 3 and 6, they both have a common factor of 3. 20/20, 40/40, they both have a common factor of 20/20, right? So they all mean the same thing, but if you look at this 1 and 2, they don't share any common factor, right? Except possibly 1 maybe, but 1 is a common factor for every number, so that doesn't count. All right, so here we can assume that m and n have no common factors. Okay, this is going to be a key part of the argument. All right, so let's just start from the beginning one more time to see where we are. We wanted to show that root 2 is not a rational number, so we went to its contrapositive. We said that, okay, let's suppose root 2 is a rational number, and every rational number is a fraction, right, of two integers. So there should be some integers m and n such that a square root of 2 equals to m over n, right? Now this m and n can be different, but if we just take the normal form, I mean the form where m and n, they don't share any common factor, then you can have just this case like this 1/2, right? So we can definitely write a square root of 2 as a fraction of two numbers m and n, where m and n don't share any common factors. Okay? Alright, and from here we'll do some very simple algebraic thing, and that will show that it's not going to happen. Okay? So here's the thing. Now, let's give it a name. Number 1 is squaring both sides of 1, we get what? The square root of 2 square is just 2m square equals to m square over n square, right? And then we can divide, we can multiply both sides by n squared. That will give us 2n squared equals to n squared. Okay. Now notice this is 2 times something, right? And 2 times anything is an even number, right? So 2n square, this guy is even. But what does it mean? That means m square also has to be even, right? But just before this problem, we did this simple proof that if m square is even, then m has to be even, right? And that gives m equals to even. So let me just write this thing. Notice 2n square is even, okay? Hence m square is even, and therefore by the previous proof m is even. M is even, right? And every even number can be written as 2 times some integer, okay? Let's say let m be equals to 2 times some number, or what can I say? Let's say p, okay? Where p is some integer. Okay, so m equals to 2p. All right, so let's give this equation a number. Let's give it 2. Okay, and we are going to substitute m by 2p in this equation 2. Okay, then from 2 we get, what do you get? On the left I have 2n square. On the right I have 2p square. Okay, so 2p square means what? 4p square. Can I divide both sides by 2? Yes, I can. And that gives us n square equals to 2p square, right? But again, you see this same argument actually pops up. Now 2p square is even because it's a product of 2, right? And that means n squared is also even. But then, by our previous proof, n has to be even, right? Okay, so let's just write this thing. I can make it really short. Let me just write it, okay? Just as above, n square let me erase this thing. Again, 2p square is even, hence n square is even, and therefore by the previous proof n is also even. But now we have produced a contradiction. What is it? Here we got m is even. That means 2 can divide m, or m has a factor of 2, right? And now we have showed that n is also even. So 2 also can divide n, so that means n has a factor of 2. But then what happens? M and n, they share the common factor, 2. But that cannot happen. At the beginning, like I had something written here in star that m and n cannot have a common factor. But now they are forced to have a common factor. And that's what we broke our hypothesis. Okay, so that's what the contradiction is. But hence M and N have a common factor two, which is a contradiction. Okay, there you go. So what have we done here? We assumed a square root of 2 to be a rational number, and then we showed that that cannot happen. We run into some contradiction. So a square root of 2 has just one choice left. What is it? It cannot be rational, so it has to be an irrational number. There you go, that's the proof. Okay, therefore the square root of 2 is an irrational number. Okay. All right, I'm going to do one last proof, and that proof is a very famous proof in mathematics, but also this is very simple and it's so beautiful. I mean, if you understand that proof, you will never forget it. Okay, so let me just show you what it is. There are plenty of proofs by contradictions which are like really awesome. I don't have time to do all of them. I have another proof by contradiction which I really like, which is called the diagonalization argument by George Cantor, which shows that the number of how should I say that? Okay, there are uncountably many numbers just in the little interval 0 to 1. The proof is not hard, but I just don't want to overload you guys, so I will stop after this proof, and that will be the end of this video. You can check that diagonalization proof by Cantor in any standard real analysis book, or I guess in many places in website. You just Google that. Okay, that's a really fantastic proof. But let's just go to our proof, the last one, and then finish the video. Okay. So the last one is a very famous statement and also proof. What is it? It is about number of primes. So what is a prime number? Let me just remind you. A prime number is a number that is divisible only by 1 and itself. Okay? Excluding 1. We don't consider 1 to be a prime number. So the smallest prime number is 2, and then we have 3, 5, 7, okay, 11, and so on and on and on. All right, now people were really fascinated by these prime numbers because you can express any numbers as some powers and products of prime numbers. But the question was, how many primes are there? So just like in the regular, the physical world, we have like 109 or some, I don't know the exact number of different, elements, right? And then they combine and then make all kinds of elements, this whole world. So mathematicians were thinking about the same. How many different prime numbers are there? Because if we know, then we'll figure out all those numbers and then we'll be done. Okay, we'll know all the mysteries of numbers. That's a very romantic idea, and just like many romantic ideas, it didn't have a very nice ending, but the proof is nice. So here is the thing. This is actually a theorem, right? There are many prime numbers. Okay, so what it says is no matter how much you try, and your son, your daughter, or your generations after generations try to calculate all the primes, it will never end. It will just keep growing and growing. In other words, there are infinitely many primes. Okay, now how are you going to prove such a huge thing, right? Are you going to figure out all the prime numbers and then say, oh yeah, there are infinite of them? But the thing is, if you can do that, then you'll be able to get all the infinite primes, right? That you cannot do. So the conventional technique to prove something will not work. This is a place where proof by contradiction is indispensable. And you'll see the power of this proof technique. So here's the proof. Just to remind you, what we did last time, in the last two problems, we just assume the opposite of our conclusion, right? So here, what are the conclusions? That the set of prime numbers is infinite, right? So we'll assume just the opposite. We'll think that, okay, let's say they are finite, okay? So let's suppose there are finitely many primes. Okay, so if there are finitely many primes, we can just collect them, right? So the first one we'll call it p sub 1, the second one we'll call it p sub 2, third one is p sub 3, and so on and so on. Okay, so let p1, p2, p3 dot 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 up to the last one, okay? Let's say p sub n, okay, be all the prime numbers. Okay, since we are assuming there are just finitely many prime numbers, so we can list all of them, right? Okay, p sub n is the last prime number, that's the nth prime number. Okay, good. But now we are going to create a new number out of them. And this is how it is done. Let x be this number. We'll multiply all of them. Okay, so p1 times p2 up to pn. We have multiplied all those prime numbers. And then we'll do one thing. We'll add a 1 with that. So plus one. Okay. So that's our new number. Now if you divide this new number by p1, what will be the remainder? It's going to be 1, right? Let me just show you the long division. So we have this number is what? p1, p2, pn plus 1, right? So if you divide this guy by p1, then what should you write here? You have to write here p2, p3 up to pn, right? So once you multiply by that, you get p1, p2 up to p sub n, but then when you subtract, you have 1, right? That's the remainder, and you cannot divide it anymore because any prime is bigger than 1. Okay, so p1 will not divide this guy. Will p2 divide this number? No, by the same analysis, right? So you have p2, then you have p1, p3, and up to pn, right? Will p3 do the job? No. Will p4? No. Will pn? No. None of the prime numbers will divide this new number x, right? Okay, so then none of the prime numbers p1 up to pn divide x. Okay, then what happens? We had all the prime numbers, and then we have a new number. None of the prime numbers divided, but of course this number divides itself, right? So what's going on? So that means that actually can mean two things. Either this number is a prime number on its own, or there should be some prime number not in our list that divides this x, right? Okay, therefore either x itself is a prime number, or there is some prime number Now this prime number is not any of those P1 up to Pn, right? Because they all fail to divide this. There is some prime number which is not in our list. That divides. X. Okay. So what did we show here actually? What we have shown here is this: no matter how big your collection is, there will definitely be some prime number out of your collection. Okay. Well, you may wonder that might still be a prime number, that might still show that there are finitely many prime numbers, but it's not, because suppose you got a new prime number here, right? You can include it there, okay, in your list. But then if you multiply here P1, P2, Pn times the new one, and then you add 1 with that, then again that new prime number will also not divide that new number. So it will keep going and going and going. So that means you will never end actually listing all the prime numbers. So that list of prime numbers is never going to be finite. So if something is not finite, what's the only option it has? That list has to be infinite. Okay, so that's the proof. Therefore, oh, by the way, sorry, I need to write this thing. What did we say? We have either x to be a prime number, or there is some prime number not in our list, okay? But that's a contradiction. Why is that a contradiction? Because we said these are all the prime numbers. There cannot be any prime numbers left outside of that list, okay? Therefore, or hence, there are infinitely many prime numbers. Okay. Alright, that's the end of this video. Next time we'll talk about the mean value theorem. Now, why did we actually talk about this proof by contradiction? Because mean value theorem is one of the most powerful theorems in calculus, and it does many fascinating things, but to show those things you need to prove things using this technique of contradiction, making contradictions, okay? So proof by contradiction will show up in great skill in next video, but until then, bye.